All right, everyone, we'll get started. Good afternoon. Welcome to, I guess, our last one before our alumni session, because next week there won't be a seminar for Memorial Day weekend. But yes, today we have, I'm going to say it, special guest, Jeremy Michalek. He was my former advisor at Carnegie Mellon. He's a professor in engineering, public policy, and mechanical engineering, and I guess now even civil environmental engineering. Director of the Vehicle Electrification Group. Yeah, so topically very similar stuff to what a lot of us do here. Yeah, and so I'll let you take it away.
Thanks. So I think the abstract and title that I gave also had a supply chain stuff on it, but I peeled that off because I talked about it yesterday. So if you really want to know about supply chain stuff at the end, let me know and I can show some stuff, because we've done some work on supply chain vulnerabilities of electric vehicle battery production. But what I'll focus on today is two things: adoption, some of the work we've done that's relevant to adoption, and there's like several different tracks. In fact, slide on that. There's several different tracks here. We'll talk about some of the stated choice work that we've done on cars, SUVs, and pickup trucks and what we're finding there. Some work we've done on economics of electrification of delivery vehicles and the potential to operate at negative cost because of coordinating routing and use of the grid. And then I'll talk about fast charging with some equity need to mention the battery degradation depending on how much you fast charge the vehicle and how much that varies by chemistry. And then part two will be about electric vehicle life cycle emissions, and I'll talk about two studies that we published this year, and then two studies that are currently working that have some preliminary results that are trying to go beyond the things we've done before on life cycle. So is it style normally interrupts the whole way through?
Yeah.
So interrupt me the whole way through. We'll talk about whatever you want to talk about. So part one, adoption. So this is work with Ken Gillingham at Yale and Connor Forsyth, who's postdoc, and Kate Whitefoot. We have a paper that was published in PNAS that I'll talk about here, and then one that's currently R&R. So these conjoint studies, many of you have seen the conjoint studies before, but what we do is ask respondents to choose among specific vehicle profiles, like here's an electric and it costs $27,000. Here's a plug-in hybrid, it's $36,000. Tell us about the operating cost, and we vary all of the attributes across different questions. And based on patterns and choices that our respondents make, we can back out what's driving their choices. The main benefit of these kinds of controlled experiments is that we know everything the respondent saw, and that we can control them and avoid correlations, all the kinds of things that plague econometric models. And of course, the main disadvantage is that only thing we can measure is what people say on surveys, which may differ from what they do in the real world. So the main thing we found in this first study is that consumers really haven't changed between us replicating the survey 8 years apart. We didn't see any statistically significant changes in their preference coefficients that define what they're willing to pay for in vehicles. Rather, the same consumers that with the same preferences are adopting more electric vehicles because the package of attributes that electric vehicles offer are just better now than they used to be. There's more range and they're lower cost. Those are the two main things. So what's neat about the fact that I should mention the first conjoint study we did, which was with John Halveston at George Washington, we were really trying to compare Chinese and American consumers. But the updated one that was in this paper, we just replicated the American consumers again. And that's the fact that we didn't see differences in what they're willing to pay for is kind of good, because it means we can project into the future potentially with more credibility. So if consumer preferences are holding pretty steady, then we can look at what those same preferences, what kind of choices would result from those preferences if technology goes where we think it's going to go. And so the only vehicle that we actually have back to 2013 would be the Nissan Leaf, and then what it looked like in 2022 and what we might expect it to look like in 2030 based on projections from a National Academy study. And over time, we're seeing the net willingness to pay for the battery electric vehicle increasing, that's in the blue, because the attributes are better. So their willingness to pay per mile of range is the same, but the number of miles of range being offered are higher, so that goes up. And then the red is the price premium, how much more it costs you to buy a BEV than an otherwise comparable gasoline vehicle, and that's coming down. And we see a crossover point coming for most of these vehicles. And so what we can do, so this crossover point, what I'm showing you here is kind of like head to head. If you had to choose between the Nissan Leaf and the Nissan Versa, which kind of the same body but different powertrain, that's where we see this crossover point coming. Simulating the entire market is a different beast because what sales look like in the entire market depends entirely on what vehicles are being offered. So we just run a scenario in which every gasoline vehicle has an electric counterpart. And under that condition, what would we expect choices to look like? And we could easily see a majority or near majority of both cars and SUVs choices being electric in 2030, just based on the technology advancements that we're expecting. Again, it's stated choice, but because we did the same stated choice experiment 8 years apart, differences in these choices hopefully are telling us something about what's shifting over time, even if there's a gap. We did the same type of study for pickup truck owners. And for pickup truck owners, we took some time to do a latent class analysis where we basically divide consumers based on patterns in their choices, not based on their demographics or something like that. But if there's a pattern in the way that in what they're choosing across these different questions, we're going to group them together based on having similar choices. And we end up in our 3-segment group, we end up being able to describe these pickup truck buyers as 3 types. The first are tech indifferent. We call them tech indifferent because their coefficients for vehicle technology are statistically 0. So they don't seem to care whether it's electric or gasoline. They care what's the range and what's the cost to operate and what's the hauling capacity. And so that's the largest segment. The second segment is electric enthusiast group. This group is willing to pay more for an electric vehicle than an otherwise equivalent gasoline vehicle. And they highly value the operation cost savings, like too highly. And then the last group is the electric opposed, about 26%. This group has very negative coefficients for battery electric vehicles. So much so that even if you made the range very long and the cost very low, and there's basically nothing you could do to win over these consumers without changing their preferences. Preferences they have are so negative for electric that the technology improvement won't pull them in. So when we do that same kind of like simulation of the whole market, we could still see a large adoption of even electric pickup trucks by 2030. It's not what we're seeing right now, but we could see that happening just based on where we expect technology to go. But getting to 50% might be a heck of a lot easier than getting to 100% because you can't get those last consumers without changing hearts and minds, which maybe we'll be able to do, or maybe more exposure will change that. But based on the evidence we have so far, we don't see consumer preferences changing that much. Yeah.
Does the price premium include state or federal incentives, or is that just the sticker price of the vehicle?
Great question. Yeah, these are, well, I think we're agnostic about that, but when we're projecting into the future, by 2030, we're projecting a price premium of 0. So that's like whether that's coming from incentives or coming from technology improvements, we don't really have to say. We're just using a 0.
Got it. So then maybe that's right. A way to then interpret this is that no matter what, doesn't matter if we have incentives or not, like, right, 50% or whatever it is, 50% of people are just going to get EVs because the technology is going to be better. So we need incentives for up to 50. So the additionality, right, of like the incentives that you're adding. Someone's just going to do it anyway, right?
Well, I would say this 50%, I still have to emphasize the stated choice, right? So we might not actually get 50% sales, but there's at least a lot of consumers who are open to electric vehicle adoption when the attributes get better. But even if you add massive incentives for the other, that 26% that's up here that isn't going to do it, you can't win them over with just money or better attributes. Like they actually have to change their preferences to adopt. Now, this whole thing is based on assuming that every gasoline vehicle has an electric powertrain option, which isn't the reality and won't be the reality in 2030. So the actual share is going to depend on supply, not just demand. And so if gasoline vehicles weren't available, then of course this electric opposed group wouldn't have other options. They may still choose electric because they don't have another option. But basically, it's like you either change their preferences or you take away the other option. Otherwise, you're not going to transition, that group. So much lower cost to get the earlier adopters, much higher cost to, there's some of these applications where it might not make sense to electrify or at least any time in the near future.
When you're saying if every gasoline pickup truck offered a EV variant, do you consider the costs as the same for the gasoline and the EVs or?
In 2030,
In 2030.
and that's coming from national academies.
Yes.
The estimate was range going up to 300 without a price premium by 2030.
Do you know off the top of your head, what are the battery price, motor price, like, in order to get that? What are the assumptions in order to get that price parity?
No, I don't know off the top of my head. I don't know that motor is the big thing. Battery is the big thing, and the battery cost reduction. I mean, battery costs have already come down dramatically, as you know, and they can't go down below material price. And so there's probably limited amount of, we can continue to shave off. But I'm not the co-author who knows as much about. Kate Whitefoot was on the National Academies panel that did that projection, and so she'd be the right one to ask about that.
I think generally they say $85 a kilowatt hour
Okay.
is the break even per MSRP.
Okay.
It's like rough,
Roughly.
obviously,
Yeah, which is like below material price, depending on the chemistry.
Depends,
So-
there's.
85 kilowatt seller pack.
Pack. Yeah.
Oh,
Yeah.
okay, I need to go back, but I think it's selling, it's 100 and something, but I'm not sure.
Work.
I mean
Of course, it depends what are gas prices.
Yeah,
like,
it depends on a lot of things, but the number.
Oh, sorry, this is purchase price, so it's not gas prices, but anyways.
Yeah.
Yeah, there's powertrain efficiency also
Yeah.
contribute to
Yeah.
that.
There's plenty of,
Okay. So the other thing was about who are these resistors? And so, as I mentioned, when we segment the market, we don't segment it based on demographics. We segment it based on patterns in their choices. But after we've come up with these segments, we can look back and say, the people who fall into these segments, do they tend to differ on demographics? And so the electric opposed group is probably exactly the people you would think they are. They don't believe in climate change as much. They come from a more rural areas, and they don't have as many DC fast chargers per capita. And this last one, it's not clear from this kind of analysis that there'd be causality. So going back to the discussion we were having earlier, if you add chargers here, it doesn't necessarily mean this group's going to adopt more. But this is a group that has fewer access to chargers. So. Okay, so that's for light duty. We've been looking at some medium duty questions, and the thing with medium duty is the fleet operator might be much more likely to make a decision based on net present value calculations, something like that, than an ordinary light duty vehicle consumer. So this is one slide on our electric delivery truck study. In this study, what we're interested in is if you coordinate the routing and charging of an electric delivery truck, can you get it to beat diesel? And so we have these different cases: East Coast Texas, Northern Southern California, and China. And the bar on the left is the range of costs for operating a delivery truck, a diesel delivery truck. And then the second bar is the range of costs for operating a electric delivery truck. And it's come out kind of light on the screen here, so I don't know how well you can see it, but it goes from down here to way up there. If your charging is not managed, you could end up with comparable costs to a diesel truck, or you could end up with dramatically higher costs than a diesel truck. And the main reasons are, number one, you end up charging when electricity is more expensive, or number two, you end up increasing the peak load at your facility, and then you end up with demand charges because the facility peak demand increases. So the next bar is if I coordinate that charging. So I decide, when am I going to send packages out for delivery? When am I going to charge? And I do the whole thing to try to minimize cost. Then I can keep that range very comparable to diesel. And vehicle to grid doesn't change the answer too much
for this first case. But when we look at California, the tariff structures are such that vehicle to grid can actually get me into regions where I can deliver packages at negative cost. So the vehicle is making enough money both through arbitrage, buying electricity when it's cheap and selling it back when it's expensive, and through peak shaving, that when the facility, like the depot, is at its peak load, the vehicle parks and gives electricity back to reduce that peak load. And those two things together are save enough money to be able to operate the vehicle at negative cost, even before you're talking about the revenue you get from doing the deliveries. So it looks like in particular, because of tariff structures, that California is like a good first area to, for electrification of delivery.
I wonder if you did the analysis, because that seems quite profitable.
Yeah.
I wonder if you did the analysis of would it be more profitable to just not deliver packages at
Not
all,
deliver.
and then just do the arbitrage and not lose the energy moving the vehicle?
Yeah.
I mean, buying a storage.
Buying a battery.
But of course, if you're going to do that, you would do stationary storage, right?
Yeah. I've been thinking about the idea also of like having a fleet of vehicles going to free chargers.
Yes.
And then arbitraging that back into the grid.
Yes.
I was wondering if you had done that.
That's a great way to get policy change.
Yeah.
Yeah. The free charging policy change.
Yeah.
So the caveats here would be
Yeah.
we're assuming we have perfect information, and that we have control over it depends on where your deliveries are located and how much flexibility of delivery time there is. Like, can you have your customer wait till the afternoon to get their package? Like, it depends. All of this. So in each of these scenarios, we use like a reasonable route for that region of the country. We look at the tariff structures from that region of the country. But of course, all of these things will vary in practice. So, but yes, according to this, you could buy vehicles, park them, and make money out of them.
Yeah, I guess just wondering about the rate assumptions that you have in here. I don't know if you know this, but do you know what goes in? Because like, if you talk about Northern California, like PG&E versus SMUD, but also like there's commercial rates at different tiers depending on all sizes of your demand.
Yes.
So I don't know if you are familiar with any of those.
Yeah, so Rami Aris is the first author of this. He is familiar with all that because he's worked in the industry.
Yeah.
And so he's built the cases based on that. But yeah, it's a great question, but I don't know the details enough to walk through that. Okay.
Regarding, and this might be a question for Rami, but regarding the vehicle to grid utilization, do you know to what extent the actual kilowatt hours that are being utilized for these exchanges? And that may be a question for him.
Yeah, that's a good question. I'm sure it varies across the cases here. And no, I don't have that number on the top. So this paper is not, actually this paper is on my desk right now to review. So probably this weekend I will know the answers to some of these things a little bit more. But yes, obviously the vehicle to grid must be doing quite a bit in order to get you from controlled charging here to vehicle to grid there, but I don't have the numbers. Yeah.
Thank you.
Good, thank you. Okay, and then the last topic that was related to adoption stuff is about EV battery resilience to fast charging. So we took a bunch of batteries and put them in a cycler, and some of them we cycle level 2 up and down. Some of them we cycle level 2 and then fast charging, and then level 2 and then fast charging. So we vary the amount of level 2 versus fast charging that we're doing across all of these cells, and we look to see how it affects the degradation. And the bottom line is that lithium iron phosphate at the top. So if you're not familiar, there are 3 major chemistries for electric vehicle batteries right now: lithium iron phosphate, nickel, cobalt, aluminum, and nickel, manganese, cobalt. That's not shown here because we're still cycling those cells. But the LFP, you can abuse it by charging it from 0 to 100%. You can do that for all DC fast charging, and you still 100,000 miles, it still looks like it's brand new. So very, very resilient. In contrast, nickel, cobalt, aluminum. So the top is what you would get if you bought a Tesla today with a standard range. The bottom is what you'd get if you bought a long range Tesla today. And if you abuse the NCAs, they can die extremely fast. And we don't abuse the NCAs that much in an actual vehicle because both the charger and the vehicle have controls to try to prevent you from being in this situation, but certainly sensitive to both fast charging and use of that. So part of what I mean by abuse is charging it all the way from 0 to all the way to 100% of what the battery's nameplate capacity is, which we usually don't do. We add buffers to make sure we're not killing the battery too fast. But with LFP, you actually can do that and still have the battery last a long time. So we wouldn't actually replace batteries every time they died continuously over the vehicle's life if it was this expensive. But if we did, this is what the numbers would look like. If I do 100% fast charging of NCA, I'm talking totally prohibitive battery replacement costs to keep replacing batteries that are being killed that fast. If I restrict so that I only use the battery from 20 to 80% and I don't actually cycle it all the way up to 100 or down to 0, that helps the battery last longer, but still 100% fast charging still results in multiple battery replacements. And LFP, you can fast charge it all the time from 0 to 100% and you get no battery replacement. So there's a really big difference here in sensitivity. Yeah.
Oh, could you talk more about how these different charging speeds are actually just like charging, discharging the battery? So like when it goes from 0 to 100%, is there any trickle charge towards the end? Is it all like full power throughout the whole charging speed throughout all SOC states?
Yeah, that's a great question. So it is a constant current.
Constant current,
Yes.
even in the last 10% of SOC?
Yes. Which is part of the abuse case.
It's very abusive behavior.
So if you ramp down the charging, you can reduce some of this, but you're doing it at the expense of charging speed, which is fine.
But most car batteries, they wouldn't let you do that, right? Like,
Mostly CC, that CB.
yeah,
so-
I know, I'm aware. So like the test site that does this testing, like is able to like you put in all the inputs for like the charging speed, voltage, power. So it's
Yeah, so Alan had sent me some of the, Alan had sent me some examples of charging profiles at different, the cars and the EDSE both control that, right? And so you end up with a lot of heterogeneity. There are some cases where there are constant power for charging, like pretty constant power profile, and that's the kind we're testing here.
okay.
As you go to those different profiles, those would affect these more. So you can avoid this kind of degradation by doing things like what you're saying, is like you just slow it down at the end. So yes, we could do that, but then it starts to get complicated. Well, which type of charging profile are we talking about when we're comparing across these chemistries? So I think we use kind of a standard, simple, profile across all the chemistries so that we can see how much it matters. And so to be clear, you don't have to end up here in an actual Tesla because you can design the controller to avoid that, but you're doing so at a compromise. Whereas here, there's no compromise to be had. Does that make sense?
Yeah.
You can slam one chemistry without the other.
Yeah.
Well, so the 0 to 100 in both situations, it's like the last 10% of SOC is very high amperage. It's being charged at very
Yeah,
high.
I understand the question you're asking. It's an important question. I'll have to check with Hannah. Hannah's the one who ran all of these cells. So this project was with Hannah Marin and Jay Whitaker. Jay's he designed batteries for the Mars rover. He's on his second battery company now. And so a lot of the details about how they do the testing, they were leading that part. So that's a good question in terms of if that last bit of charging is at full blast, that type of abuse may be too non-representative. That's basically your concern. And yeah, which is fair. Yeah, so let me, why don't you follow, if you send me an email about that, I can get an answer to you. Yeah. Yep.
So in when you design this experiment, did you look at different charging profiles, different buffers that are in place with different ones, so VPs, and also different sensors, but temperature sensors to prevent some charging speeds from exceeding during charging processes? Were you able to look at what different points would offer integration and the batteries are not that we still want?
No, that kind of goes back to the same question that in this experiment, we're running them all the same way. And there are many ways that you could add these additional safety mechanisms and slowing down to make the battery last longer. And we don't test all of those because we've only run so many cells. It's more, So I think the critique is good that if the difference between these two chemistries may be much smaller under typical protections that are in real charging profiles. I think the other way to think about it here is, I don't know that we need those protections for LFP. And the whole thing about LFP is that it is a, it's a less energy dense chemistry. And so but you can use more of it and you can charge it faster. And so it to some degree, it sort of mitigates that disadvantage because of the different, potential that it has here.
The cost here, one more, maybe I missed it. The second scenario is the same battery or it's a 40% bigger in kilowatt hours?
Same battery.
So it's actually a lower utilization.
Yes, and you cycle it more to get the same number of miles. I mean, I think in this graph before we, this is not the latest version of this graph, but anyway, we convert everything into equivalent miles. And so if you have a smaller state of charge window, then you have to cycle it more times to get the same number of miles.
Other option would be to have bigger nameplate, bigger battery.
Yes, but these are individual cells, the 18650, so
I see.
we're just cycling them less.
Yeah.
But you're right, if there were more of those cells, you'd be doing that too. Yeah. Okay. So that's what I wanted to cover on adoption related. Oh, sorry, I didn't hit this one kind of equity related issue, which is just that one of the things that worries me about this is that the second owners of EVs are going to get a used battery that's partly degraded. It's really hard to know how much. I have a EV that I bought used, or a plug-in hybrid that I bought used, and that was a worry, still is. But that second owner is also much more likely to live in a multi-unit dwelling or otherwise not have off-street parking. So they're the ones who start using fast charging more. And so if they have LFP, that may not matter. Whereas if they buy an NCA or chemistry and it's partly degraded, and then they start adding the fast charging too, then that owner could see that things degrade really fast. And so one of the things we're thinking about is like, well, what do we do about this? Because I don't know that consumer education I don't know that we have a great route to that, because I do not see consumers like knowing which lithium ion chemistry they have. That's not going to happen. And furthermore, this is not all LFP cells. This is just the ones we tested. So there may be more variants than we can figure out in this experiment. So, but this seems like a big deal is even if the control strategies like don't get this bad, you still could end up seeing, the second life batteries not last, or second hand vehicles not lasting as long, particularly because if they get fast charged more often. Yeah.
Does the costs at the 100%, the worst case scenario, I think this is like the worst case scenario for batteries. To me, this might suggest that for like if I'm an automaker, I think there's like no one's gonna replace the batteries, way too expensive. Like, well, I'm just gonna recycle it. Right? So it's actually like this may actually for certain scenarios where NCA is cycled in a way that causes this damage to the cells, it actually makes
the value proposition for a cycling battery higher because they're not going to work. Like the consumer can sell it back, or there's something lease offtake at the end of the ownership, the lifetime of battery, the life of the ownership of the vehicle. Versus like LFP, it's like, well, you're probably just not recycle those. So those just kind of keep going. Right.
Yeah.
So you're going to have maybe a recycling industry that's more dependent on certain chemistries that are just inherently, or I shouldn't say that, just have the propensity to experience a worse degradation just based on how they're used.
I mean, both of these types of batteries will reach end of life at some point, and then there's a recycling decision. I actually have a different reason why I would agree with you. I think this one's going to be recycled because there's nickel in it, and that's what's going to drive the economics of the recycling process. I think this one's not, because there's not anything valuable in it. Lithium, you want the lithium out of it, but is it worth enough to drive the economics of the recycling process? So that's actually a project we're just starting now, is looking at end of life. Because you're saying, well, this one lasts forever, but at some point the vehicle goes to the junkyard and the battery, something's got to happen to it, right?
Yeah, I guess, I just see
at least in the short term, the recycling industry for batteries will depend on certain chemistries more than lithium because it has a longer life cycle. But I wonder with lithium iron phosphate, it's like, yes, not as valuable, but like you can recycle lithium a lot. And once you bring it in the United States, it's US lithium, you don't have to like mine or of it. It's like we secure.
Yeah, but you still need a
our-
business that can make money to like, otherwise you won't. Either that or you need a policy that drives it, like take back rules or something like. So that's what I'm interested in now is like, if we've got all of this materials that we're importing that are critical materials. That's the other talk from yesterday. There's China is heavily present in many stages of the supply chain, from materials refining to cathode production, and recycling eventually will be a way to displace a portion of the import needs. So that's going to look really different while we're still ramping up, which means the number of old vehicles is very small compared to the number on the road, right? But even in steady state, you can get a certain amount of these materials back through the recycling process only if it's driven by something. And so my sense is with this one, it all depends on the price of nickel, but often nickel can drive, make a business out of recycling. But I don't think you can make a business out of recycling this way, although I haven't done the analysis yet. And so my question is, well, there are different policy levers you could pull to make recycling happen, but that doesn't necessarily mean that's the best thing for society. It kind of depends on the cost and the benefits. So that's kind of what I want to figure out next is like, is there a case to be made for policy that would drive that circular economy, or is the costs outweigh the benefits? Yeah.
This is very interesting. I also saw this at the policy council meeting at Tubing. Can you go back one to the traces?
Mhm.
So the top trace looks like exponential decay, which is what you would expect, I think. But the bottom trace is like a very different pattern in like the way the decay goes after the knee. Like, did you test a lot of batteries to get, and like, is this the average of those or?
No, each one of these is the average of a few cells, I think.
A few cells? Okay.
I'm not sure about that. That's a good question. I'll have to check.
So like what, I guess like.
This is very common degradation
It's
pattern.
very common? Okay.
Yeah, you degrade to a certain point and then different mechanisms come in and then you
Okay.
die really fast.
Got it.
Yes.
So,
LFP is different because the mechanisms of degradation, it's a lower voltage cell.
okay.
And so a lot of,
I'm
I'm getting beyond my knowledge here, but
a lot of the chemical reactions, so like there are multiple ways that batteries degrade. It could be in the anode or the cathode. There could be like side reactions that, especially at high voltage. So I'm agnostic about what's happening inside the cell. It's not fully understood, but I think the mechanisms going on in LFP, there's been prior work that suggests this degradation is pretty much every amp hour you process degrades the battery X amount.
Okay.
Whereas here, it's much more dependent on, well, what's the state of charge and what's the C rate and what's the temperature, and all of those factors can affect how it degrades and when you hit this kind of B point.
Okay. Well, thanks.
I just want to say that on your next slide on the scenario, it's not theoretical anymore. Now we're going to study the secondary market. You can buy a year or 2 years old Tesla with 80,000 miles coming out of TNC, all fast charging, or a 4 or 5 years old Tesla with 80,000 miles that was all slow charging.
Yes.
And buyers today will have no idea how different the results can be. They both have 80,000 miles on them.
Yes.
So there is a lot of policy that we need to kind of take your results and try to think how to bring it to the buyers.
Yeah, and I don't know how to do that because like really the battery is a bit of a mystery. Like you don't know its degradation history, and even if you knew it exactly, it's like how different modes of degradation add onto like prior modes of degradation is still like it's a bit of a black box.
Yeah.
So I don't know that we know enough yet, and maybe we're counting on like these things have gotten so robust that they'll just outlast the life of the body and then we're fine. But
what you're saying that if they both have 80,000 miles, can be very, very
it can
different.
be very different, yes. So the whole thing is, I mean, like if you avoid this and you avoid this, or if you're going to do this and you use a more gentle charging pattern, maybe you still get zero.
Or maybe okay. Yeah. So I kind of think of policy implications that we will study in the context of in the context of the adoption.
Yes.
Promotion of basic fast chargers, and looks like, if you look at the worst case scenarios, there's no charging condition out there that has like the abusive scenarios that you tested in this case. And do you think, I mean, we already have a potential EV bias who are comparing battery degradation to the battery degradation of mobile phones, because that is an many protections above as well as EVs and the charging station constantly communicate like 10 hertz per second of what are the maximum charging speeds they can do without creep so much. Do you think in the context of informing real world policy, this might give like a wrong impression to policymakers that we shouldn't be doing these fast chargers and common with?
Well, we did not write a policy brief saying that. So no, I don't think I would take that lesson from this, that we should not be doing DC fast charging, even if these results were unavoidable in real world and, that real fast chargers were doing this. I don't think that would necessarily say we shouldn't do fast charging because it's trade-offs.
Do you think maybe like the battery storage business model might make more use of this as opposed to EV charging?
Maybe what I should do is collect data on the different charging profiles that are used in practice, compare them to what we're doing, and then I can try to make a clearer case for to what degree this is unrealistic abuse that won't happen in practice, and to what degree it actually is close to things that happen in practice. And that would be helpful for figuring out how important this is on a policy today level. But I think that charging profiles are not set in stone yet. We don't have a standard for that. They're completely different in different chargers and different vehicles. And what this is suggesting is that if with the right chemistry, you can charge faster, and with the wrong chemistry, maybe you're going to have to stick to these conservative charging profiles. But I mean, like, we're really trying to push for like, can I please charge in 8 minutes instead of 15? Like, it really matters, right? And so I think there's potentially a difference here in terms of, how much you can abuse them. But I think your point is really good, that without a comparison to a variety of fast charging profiles, it may be hard to know how to compare this to like what's happening with vehicles today.
What are things like paper will test all the assumptions in the text, but then people will just read the title and the.
Oh yes, I'm very familiar with this concern. Yes. Yes. Point taken. Okay. So let me talk about EV environmental impact, and then you can ask that question again about are people going to misinterpret these results and make the wrong decision. I've done life cycle work on electric vehicles since I think I started in 2007. So I've been thinking about this issue a lot. This is, I'm not giving you the result here. This is from 2019. This is specific to the PJM part of the grid, which is in the east. But I'm just sort of pointing out that in a life cycle, we think about emissions for vehicle production, battery production, gasoline production, as well as vehicle use, which includes tailpipe emissions, as well as tire wear and all the other things that happen while you're using the vehicle. And we also, many studies will focus on greenhouse gas emissions because it's the thing we're all worried about, right? It's the existential crisis we have to solve. But actually, it's not the only factor that matters. Like air pollution matters too, and there are other factors that matter as well. So in a lot of our studies, we leverage models of the health damages from air pollutants to try to monetize social costs of carbon, put them together, and figure out what is the total net external costs associated with these different vehicles. And none of these are negligible. I mean, battery production's often small, but when you get to a big battery electric vehicle, it can be quite substantial. It depends on the chemistry, depends on how much nickel you have. Of course, I'm sure almost all of anybody who works in this area would know that power grid emissions vary regionally, and electricity is traded across large areas. So it's in life cycle assessment, whenever you have co-products, like you have a facility that produces two things, you have to figure out how the emissions from that facility gets divided among those things. Well, it's never a bigger problem than in electricity, where you've got tons of generators feeding into this massively interconnected thing, and then tons of sort of demand pulling electrons out of that, network, and you just can't trace electrons, like which power plant my electrons came from. So we have to be careful what question we ask when we're thinking about life cycle assessment. And I was on a National Academies committee that wrote a consensus report about this. And I have to say, it was a diverse committee. We disagreed on a lot of things. And nice thing about National Academies is the report that you write, everybody has to sign off on it. So the only words in this report are things that all of us could agree on, even though we disagreed about much. I think the most important thing that we try to clarify in the report is this distinction between an attributional and a consequential life cycle assessment approach. Economists think of this as like marginal emissions, but really marginal means for small. Consequential is more general, could mean for big changes as well. So what I mean by attributional is if electric vehicles are X% of the load in a region, then assign them X% of the emissions. So that seems fair. The only thing is, it really depends on what you define as the boundary of the region. I mean, any boundary you can draw around a region, there's trade across that boundary. And so, if I charge my electric vehicle in Pittsburgh, is it the power plants in the city of Pittsburgh? There aren't any. Is it in the county? Is it in the state? Is it in the NERC region or the RTO? Like, any boundary you draw is arbitrary and power flows across it. And you can get extremely different answers depending on what boundary you choose to average emissions over. The other thing is it doesn't really answer the question of how a policy change will affect things, or a change in adoption will affect things. And depending what question you're interested in, I think if you're interested in a policy question, like should I pass this policy or not? What will be the effect of passing this policy? Then you're interested in a consequential question. Consequential means you need some way to model what the world would do if you add this PEV load and what the world would do if you don't add this PEV load, and then the difference between the two is the consequences of adding the PEV load. So I've done studies on each, but I've really been much more focused on consequential because I'm trying to understand if I have a decision to make about adoption, increasing adoption, or doing a policy that will increase adoption. I want to understand not just what the emissions look like today, but like how that action will change the emissions, because that's like the effect of taking that action. So we've got a few studies on these, one in ES&T, where we had looked at like how much cleaner does the grid need to be in order to ensure that the electric vehicles beat even the most efficient gasoline vehicles, like gasoline hybrids. I think Alan kind of hates this study, but but if you compare like a Nissan Leaf to a Honda Accord, the grid's clean enough everywhere, and the Nissan Leaf's cleaner than the Honda Accord on greenhouse gas emissions at least. But if you compare a Tesla Model S to a Toyota Prius, well, the Tesla Model S is worse than the Toyota Prius in most of the country today. You would need cleaning of the electricity grid to beat. So are we beating the average car? Yes. Are we beating the best gasoline car when we go electric? Well, it depends. I mean, it depends where you are and what vehicles we're talking about. And so one of the issues that we think a lot about is how much heterogeneity there is there. When people are doing a life cycle assessment, they'll often use the GREET model, and it just has like a representative vehicle from each type, which is fine, but really there's a lot of heterogeneity within each group. And so thinking about that heterogeneity has been part of our efforts. Go ahead. Yes, Gil.
I read this paper. I
Yes.
don't hate it like Alan.
Yes,
but
good.
I
Thank
think
you.
I like it. Yeah, you started. But I think you misrepresented Tesla versus the Toyota, because most of the cars are coming better as Tesla. Not most of the land of the US or most of the area, but most of the cars
Most of the cars are.
better to be a Tesla and not a Prius on this scenario. So it's by colors on the map you have, but I think
You're saying where the population is?
yes, the population of vehicles.
But even blue here is a positive number, which means you would need a reduction. Maybe that blue is 100. So yeah, a lot of people live here, but that's still 100.
And then you have New York. Okay, maybe. Okay, yeah. Yeah.
So
it's
yeah,
only
I
the
get your
white.
point. It's
Yeah.
like this area, like where things are worse in MRO, nobody
There's
lives
no one
there.
there. Yeah.
Yeah, right. So point taken. But
Yeah, but yeah, maybe you're right. Okay.
And I would draw the state and nobody lives there because like real human beings live there. But
Yeah, we're recorded.
it's very like it's not very dense compared to like over here. And the Model S is not your average Tesla, right? I mean that's a unique vehicle, which is why I said Alan didn't like that comparison. I will mention the reason we picked these particular vehicles is because we needed vehicles that had been tested in temperature control chambers so that we could capture the effects of temperature on efficiency, because it really matters if you live in a cold region or a very hot region, primarily because the HVAC, but also because battery efficiency changes with temperature. We were trying to account for all of that, so we were limited to the set of vehicles that Argonne had done testing on. Since then, they've done a bunch more vehicles, and so like it was too late to get them in the paper, so there's like a blog post that has like other vehicles in there now. Yeah. So, but those maps were just for greenhouse gas emissions. And as I mentioned before, I don't think we should focus on just greenhouse gas emissions. It really, like, we want to reduce greenhouse gas emissions, we want to reduce them a lot, but there are trade-offs, and we don't want to ignore the trade-offs. So, to get into GHGs and air pollutants, we want to restrict our scope to, with air pollutants, it matters where they're released, so you actually have to know where the power plants are located, so it's much harder to model, like, the entire country. So we focused in on the PJM region, which includes Pittsburgh, where I live, but it spans from Chicago to Philadelphia to North Carolina. And it is the biggest regional transmission organization. It serves, I think, 13 states in the District of Columbia. And the power grid mix in PJM is pretty similar to North America as a whole. In fact, one of the reviews I got on this paper, probably from a Californian, was like, oh, you're studying a dirty coal grid, you know. And so I made this figure just to respond to that. I was like, no, California is the outlier. This is what the world looks like right now. Coal is part of the picture for most of us. Yeah.
Well, do you know what the generation capacity is in PJM?
I'm just curious as a comparison.
California's like
The peak.
the generation capacity, right? Not talking about deploy, because California's around like
55 kilowatt.
Okay, no, I don't know, but I can find out quickly. Yeah.
185 gigawatts.
185.
Yes.
Oh, that was
You
way
can find out quickly. That's good.
That was way bigger than I thought.
So we did a study in PJM, coal heavy compared to California, back using 2010 data. This is an older study. And we had found that if you drove a Tesla in our region of the country, you'd cause about 2 to 3 times the air emissions externalities as a gasoline vehicle. That largely is because of sulfur dioxide emissions from coal-fired power plants, because they get into the atmosphere, turn into particles downwind, and then people breathe them in, and then they get cardiovascular and respiratory diseases. And so we monetize all of those things. And what we did this year, or got published this year, it took us 3 years to do it, was to update that study. And so the most recent year where we had all the data we needed to do that study was 2019 grid data. And we predicted based on the old study that things were going to get better as coal retired. And they did. They got a lot better. And using what plants are on the list to retire and to be built, it looks like by 2025 they'll keep getting better, and then in PJM will be comparable to gasoline and battery electric vehicles will be comparable. Where they go in the future, we ran a zillion scenarios to look to see what matters most in determining where they're going to go in the future. The base case really flattens out. And the reason it flattens out is because we can, as we're building more wind and solar, coal and gas are still in the margin. Like, it doesn't change what, like, basically we have all these power plants, like wind and solar, are just generating as much as they possibly can. This is even still true in California, as far as I understand. I know we have a duck curve, but I'm not sure how much curtailment you really have compared to overall generation. And so it really, like, if you add new load, you're not adding the amount of wind or solar that is generating. You're adding coal and gas generation, because that's how the system responds to changes in load. It's already generating as much wind and solar as it possibly can, and nuclear. So it's really like fossil fuels that are at the margin. So that's why it flattens out how much better you can do. So across all these scenarios, the scenarios that are down here that look best, the biggest lever over the next decade is really battery chemistry. Now, in the really long run, replacing fossil with renewables, entirely or whatever, yeah, then this picture is completely going to change. But in the next decade, we're not at that point yet. We're still at the point where fossil fuels on the margin. So the best scenarios involve a switch to lithium iron phosphate chemistry, and that's because it doesn't have nickel. And nickel's the primary reason, because in nickel production, you also have a lot of sulfur dioxide emissions, which, depending on the country, are sometimes controlled well and sometimes not. And so when they're not controlled well, then they kill people downwind. And so that's getting away from nickel helps bring you down to here. So kind of a neat thing about this, I forget if I have this on the slide. Yeah, a neat thing about this is that in the last year, we've had 3 totally separate studies looking at different things that have all pointed toward benefits of LFP. One was about it being super robust to fast charging. One was about the best life cycle scenarios we see involve getting nickel out of the batteries. And then the third is that I talked about yesterday is that LFP only has one critical material, lithium, whereas the other batteries also have to source nickel, cobalt, and sometimes manganese. And that creates additional vulnerabilities in the supply chain where, you can end up with a country, spiking the cost of those materials or shutting off the exports and have a disruption that you have to manage. So there are other reasons that LFP might not be the best for every application, but these are at least 3 reasons that are all pointing toward a benefit toward LFP, which luckily is kind of where the there is a shift toward LFP right now, which I think, at least for these reasons, is a good thing. Yeah.
For the life cycle air emissions, are you choosing some kind of static representative vehicle model, or is this meant to represent average vehicles in the fleet? I asked that, right, because your ICE and AGV lines are flat.
Yes, that's a great point. So in the past study, I just talked about how heterogeneity of vehicles matters, and then in this study, I didn't do heterogeneity of vehicles. But the vehicles are identical across all these years. The only thing that's changing is the generator fleet scenario. So we're not really projecting what vehicles are going to be in 2035. That's a bunch of new assumptions we would have to make. This is given a static vehicle, what's going to change in the grid that would, and maybe that's a little too strict because we are changing the battery chemistry in the vehicle, but we're not changing the Tesla Model S to the Tesla Model 3 or something. We're not changing what the technology is.
Yeah, because it's because the big thing for me would be efficiencies improving for gas vehicles over time, and then for EVs, there's stuff you're introducing vehicles into larger format classes so that maybe the efficiency down.
Yes.
But
I think those are all good points, and intentionally what we wanted to do here was isolate the effect of the grid, and we're not trying to model all the things that might or might not change over the time frame. We're trying to say, holding those things constant, what changes in the grid and what would those effects be? So, it's pros and cons because when you try to account for everything, then it's a soup of assumptions and it becomes harder to, we need those studies too, but here what we're trying to do is isolate this one factor that we can know really well.
Yeah.
Yep. So, how am I on time?
We have till 3, and then
okay.
There's you can leave some time at the end for questions.
Okay, yeah. Sounds good. So I'm going to show you 2 studies that we're working on right now. So the results are preliminary, but we're trying to get one step beyond what we've been doing in those prior studies. And let's see, David Brapson's still online. So David, I can mention we had happy hour yesterday. We were talking about this. One of the critiques of the prior work that we've done on this is that we're only looking at how a given grid would operate differently if we adopt more EVs. That grid might be changing over time, like in the last scenarios that I showed you. I am assuming the grid is different in 2035 than it is in 2025, but I'm not assuming the electric vehicles made it different. I'm just assuming it has some trajectory of evolution, and then if you add EVs to the system, then those plants will operate differently. Well, the critique had been, if you add EVs to the system, you might induce changes in the kinds of power plants that get built. And this is has been a qualitative critique. It was like, oh, everything will be fine. It's green because you add EVs and you'll get wind. It's fine. But I wanted to know, like, is that really true? And if so, how much? You know, is that enough to change the answer? So we have two different ways that we're trying to get at this question. The first is with Lily Hanig, where we're using NREL's model, which is called READS. That's the model that's underneath Cambium. There was a nice discussion in PNAS where some of the economists who've been working on this study had done these marginal emission factors and showed that marginal wasn't changing, that even as the grid was getting cleaner, the margin was staying pretty dirty, which was exactly for the reason I was talking about before, because fossil stays on the margin for a long time. And they got a critique comment that was like, you're missing the induced ability of EVs to cause us to build more wind than we would have otherwise. But I think the way they tried to model that wasn't quite right. So I'm trying to do it what I think is right. And so the way we're doing it is looking at the different trajectories of what EV adoption could look like. The baseline is the IRA scenario. And then we have like Biden's targets, what EPA suggests based on their the new light-duty vehicle greenhouse gas standards, a net zero scenario, and on the other side, the AEO, the annual energy outlook from 2023, didn't include IRA, so it's even like lower adoption levels. So these are different levels of the trajectory of EV adoption. And my question is, if we have a higher level compared to a lower level, how's that going to change the emissions in the grid? Will having more EVs, will it cause us to build more wind? Is that right or not? How much? And what does it matter? How does it matter for emissions? So we're using IRA as the baseline. This bottom set of graphs is the change relative to IRA. So that's why this one is blank, because that's the baseline. If we go from IRA to Biden, we're adding more EVs. And we're using this READS model to figure out how the grid would adapt, or at least to estimate how the grid would adapt if we have those extra EVs charging. And what you see is an increase in wind, solar, storage, and some natural gas. And that continues. As you add even more EVs, you just get more wind, solar, storage, and natural gas. And when that extra capacity is there, it can generate not only to charge the EVs, it can generate to charge, once the capacity is built, it can generate to serve many loads. We can do this regionally, and basically the bottom line here is that mostly what you're seeing in terms of the change in generation induced by these EV loads is either blue, which is wind, or yellow, which is solar. But there are some regions that are still, primarily adding natural gas in response to the new EV load. Whoops. And so what we're trying to estimate is what are the net emissions consequences of EV expansion if you include the new plants that were built because of the EVs. And in early years, they can really depend, but they quickly converge in these different scenarios with more EVs to come down to fairly low emissions per extra electric vehicle added, especially compared to a typical gasoline vehicle. You get much lower emissions per EV added. And what we're in the process of doing right now is trying to do a fair apples to apples comparison of these numbers to the kinds of marginal emission factors that are in the literature, which is a little tricky to do because marginal emission factors can change by year and region and these kinds of things. So that's why I don't have a really clean comparison here. But I think broadly I could say these emissions consequences of EV charging are lower when we account for the induced capacity expansion than if we didn't account for the induced capacity expansion. So this is one way we're trying to get at that question. And again, this was just GHGs, but I keep saying air pollution matters. So in the second one, we're trying to do that with air pollution, going back to our PJM model, where we can know where all the power plants are. And this one's with Jiahui Chen, Michael Craig, and Parth Vishnu at University of Michigan. And what we're doing here is like for all these different potential levels of variable renewable energy, this graph is for wind, so replace VRE with wind. For these different levels of capacity I could build, how much would it cost me to build that, which is the diagonal line here, medium, low, or high estimates, and how much revenue could I generate from my wind. And when I don't have any battery electric vehicles, there's some revenue curve. The more wind I have, the more revenue I could gain from that wind, but it's kind of diminishing returns. Like it's like it doesn't pay past a certain way, it doesn't pay for itself anymore. If I add battery electric vehicles, but I don't control the charging, that's the purple line. That means we assume every vehicle charges after the last trip of the day. I think we were talking about this with like the MUDs, that like everybody arrives home between 5 and 7 or something. So that would be that. All the charging starts right there. There's a very slight increase in potential revenue, but not much. So basically, you don't build any more wind just because of those EVs. But if those EVs use controlled charging, where they allow the grid operator to decide the timing and rate of the charging in order to minimize costs, with constraints, you can only charge when the vehicle's plugged in, it has to be fully charged by 6 a.m., those kinds of things. Then you can get more revenue, which makes it profitable to build more wind. Like the place where cost and revenue cross is the point at which building more wind would not be profitable. So you move that point and you induce or you at least make it profitable to build more wind than you would have otherwise. And that's particularly true with V2G, which is the, sea green color here. You can induce a bigger change, make it profitable to build even more wind. Yeah.
How much does the market structure, PGM, which is a capacity market, influence that outcomes you see here? Because if you ran in an energy only market, or if you ran in like California's quasi energy capacity market with our RA commitments that we have, like how much does this actually change? Because in Texas, if you're ERCOT, you're running strictly energy, right? And that price floats. You're capped at I think 9,000 now or something, or roundabout. But if it just floats, like your trade energy not working on necessarily on capacity, a capacity perspective, I guess. And so I'm curious if you're control, like for V2G particularly, this to me it wouldn't seem that on an energy market you would necessarily earn more revenue as a generator. I don't know if you lose money, but I don't know if it'd be the difference would be so stark as it is here. I think the difference in market structure dictating how much revenue you get as a generator only, because there are two different sides to the market, the demand and supply side, right? So I don't have like a clear head for further study, that kind of thing. Yeah.
So let me clarify what's underneath these. We're using that same optimization model of PJM that was behind the prior results that I showed as well.
Yeah.
We're not really modeling how the market's clear or anything like that. What we're doing is saying at every moment in time, which generators should be on and running at what level in order to meet the demand at minimum cost. And we're optimizing 2 days at a time and then sliding the time window forward 1 day and optimizing the next 2 days. And we do that so that you're always making decisions for 1 day with some look ahead about how those decisions will influence the next day. And there are constraints about like ramp rates and minimum on and off time, and there's reserves and things like that. So with all of those, we're modeling a lot of where the costs come from, and the revenues would be like what the they're not based on modeling a mechanism like with LMPs or something like, I don't know what level we're talking here, but they're just based on how much of the wind would end up getting curtailed because it's not being generated at the right location and time where it could be used.
This is perfect information. But then this is perfect.
Perfect information for 2 days.
For 2 days. Okay.
Yeah.
Yes. But I think this is a slightly different question, right? Because it's like, all of those aspects you're talking about are like operational aspects as opposed to like a decision about building new capacity.
Yes.
So like how does the decision to build new capacity work in this?
I see. Yes. Yeah. So I think I don't know. I guess I guess the bottom line on here is that there is a gap between revenue and cost that suggests there's money there. But that doesn't mean that wind will be built because there's money there. We look at what happens if it is, but there are like economic decisions that might be mediated by some of the mechanisms that you're talking about, like some of how the market is structured, that I'm not considering at all. But there's also totally non-market reasons too, like political or regulatory constraints or those kinds of things that might determine what actually gets built. And I don't model those either. So all I'm saying is that if you have EVs with vehicle to grid, it creates a bigger gap. Like you could build up to this much before you start losing money, but I'm not saying like a given wind plant could make this much. That might depend on these market structure questions that you're thinking about, which I'll have to talk to you more about.
Yeah, I guess I'm less interested in the total amount of money.
Yeah.
Or the absolute amount, and more interested in how does the market structure dictate what is built, and how does that, or how do EVs induce the capacity build out? Because you it was on to my tongue, but like
that's not always market driven, right? So I think that the way that REITs work, it's been a while, but for their capacity expansion part, I believe it basically does. The reason why the resolution is a little bit lower is because it's very complex to be able to understand how new capacity is going to get amortized over its lifetime. So then it makes the decision for that depends on its operation. The decision to put in a new generator depends on that generator's operation many years into the future, which is what makes capacity expansion problems like particularly computationally difficult if you're doing it in a purely economic sense. And I think what Peter is pointing out is that oftentimes new capacity isn't always made on the basis of like pure like economic decisions that I think the way REITs is doing it. So even something simple like an RPS requirement, right? Like that is not an economic decision necessarily for capacity expansion. So there's a question of like how much those kind of constraints are represented by this particular version of REITs, because I know that REITs has like a variety of versions that some consider and some don't.
Right. So to be clear, REITs was the prior study. This is not REITs.
Right. Okay.
So REITs is, I know I'm covering so many studies, it's like hard, but this stuff is all from REITs.
Yeah.
And REITs definitely does include policy constraints and like some of the weird behavior you get with AEO, the AEO case in the later years has to do with whether a policy sunsets or not based on whether a metric has been made. So some of the results can be like really specific to how a particular policy was designed. And to be honest, this one is more of a black box to me. Like Lily knows some more of the details, but we intentionally used it because the critique in PNAS was based on this model. But what I didn't like about what they did was they treated it as like a 5% across the board increase in load and then looked at the effect of that. And whereas we wanted to look at actual patterns of EV load are going to have a very different impact on what kinds of power plants it would make sense to build, and we wanted to understand what those were. But we're basically adopting all the same assumptions from REITs, and I am not the author with the deepest understanding of those REITs factors. This one is our model that we built ourselves, and so I know this one well. And so here we're looking at where there's economic. I guess the leap is: are we actually going to move? Are we actually going to build exactly this much wind in the case with no EVs? And are we actually going to build exactly that much wind in the case of EVs with vehicle to grid? Well, if you believe that, then I can show you what the emissions would look like. But I'm just showing you here where there's economic incentive to build more. I'm not saying that it will always be built because there's economic incentive. Yeah. So yeah, go ahead.
In this study, did you consider the distribution grid limitations? And if not, I was wondering how much you need to sacrifice of these, for example, 81.1 gigawatts in order to consider the distribution grid constraint. Because if we have a capacity, but if we do not expand the distribution grid, you can charge a vehicle, all of them, with the V2G or the smart charging?
Yeah, that's a great question. So, so two things. So one is I am just assuming that in the V2G case, that all the vehicles can sell back to the grid from home, which is not how it works today in most of the countries, you know. So, and not only that, but even if it did work like that, I don't see any realistic scenario in which everybody does vehicle to grid. I mean, it's just not, there's not enough incentive there to get all vehicle owners to participate. So this one's pretty optimistic, but it does say the finding that I think you should take away is flexibility matters. If the charging is flexible, even if it's just in a simple way where there's a timer, you know, it doesn't start charging at 6 when you get home, it starts charging, you know, at 2 a.m. or something like that. That some of those things, I mean, for wind and solar, wind in particular, it's particularly helpful if you can slow down the charging when the wind dies down and speed it up when the wind, you know, so you can absorb some of the curtailment. But that flexibility can potentially induce new, if you don't think that flexibility is going to be here, then you're sort of here, we're back to the case where like capacity expansion's kind of negligible, so then all of our old studies are good enough, you know. So, and then the second part was about distribution infrastructure. And my impression had been that distribution infrastructure upgrades are a real thing, and at local levels that matters, but that it's such a small, like I don't think about it as being like a big part of the overall cost.
No.
And you think
No.
complete opposite.
Yeah.
I don't think generation and transmission is big. I think distribution is like
Distribution is the
way
biggest one.
bigger peanuts to pay bird.
Okay, I will. Good.
Digits.
So, so I think this is my last slide, but what comes out of this is if you move from no battery electrics to making 10% of the fleet into battery electrics in PJM, and you do it with uncontrolled charging, you increase emissions a bit. You increase grid emissions a bit. I'm not talking about the life cycle here. If you do controlled charging, you can bring those emissions down and even get a slightly net negative. And in particular, if they were all doing vehicle to grid, and again, in that optimistic scenario where all the vehicles at home could do vehicle to grid, you can actually add load to the power grid and get a reduction in emissions. Really counterintuitive, but like, you know, there's more load, there's more generation that happens, but because of this effect of building new renewables, and then those renewables are used for other loads as well, you actually get more load. More load results in net negative reduction in emissions. So yeah, flexible charging, important. Another thing I might highlight here is that in the prior study, so one of the big uncertainties when trying to do these externalities and weigh greenhouse gas emissions against the health damages from criteria air pollutants is what is the social cost of carbon? And there is definitely no consensus on what the social cost of carbon is. Interagency working group used about $50 a ton as a baseline. That's what we used in the prior study. This, what is being shown here, because it's the only graph I had available, is using $200 a ton, which is closer to what RFF has said recently. If you change the number, you change the results. And so it does become hard to compare. Like right here, it looks like GHGs are big and air pollution is small. That's true at $200 a ton, but at $50 a ton, it's not true anymore. Air pollution is often at least as big as greenhouse gas emissions. So it really does depend on how we monetize. And I think that for the health damages, the monetization's pretty, you know, much narrower range. But for greenhouse gas emissions, in fact, Ranger Morgan has a whole paper about like, we're never going to know that number because they're all based on these biggest simulations with lots of levers that we, you know, so we shouldn't even think about it that way anymore. That's just a case where the typical way of thinking about cost benefit breaks down. And we just need to think about it as more of a wedges or, you know, something like that. The economists would say, no, like you might not know what the cost is, but there's a range, so let's look at the range. It's just that here the range can flip which way the answer goes. So, yeah.
It seems like the NOx, the SOx and Q2.5 is like marginal changes, right, across the board. And that's just because there's always a certain amount of spinning generators just beyond your good frequency. But is that the case? I get within the model operated, like you're just always going to have that. And so EVs actually, what they're helping is capacity expansion for renewables, but it's not really eating into the pre-existing thermal generators that are on any given grid, and actually the replacement of those is not going to be an EV thing. That's just simply something's cheaper, we're going to replace it, or there's a policy thing, right?
I think it's an optics thing. You can see the change in the GHG bar more because it's way up there.
Yeah.
But this change from here to here is still like 5% or whatever of the entire load of PJM for all the things they're charging. So what I've asked for and don't have yet is a version of this graph where we just show the delta between each of these and the baseline, between this and the baseline, between that and the baseline, because then you'd be able to see more clearly how much these things were changing. Because here the scale of all the things PJM is generating electricity for compared to like how much that gets changed with 10% battery electrics.
Yeah.
You know, yes, it looks like a small change, but it's per electric vehicle, it's still
Yeah, I
substantial.
guess in billions of dollars, right?
I mean, percentage-wise, those deltas might actually be pretty similar.
They might be similar,
Yeah.
yeah. It's kind of hard to tell with it stacked because the blue is shifted down and shrunk and it's
Exactly.
so I need that delta graph and I probably have it this weekend. So I think that is all. I was just going to mention that we do a lot of work to try to tie our research to policy relevant findings, sometimes studying policy directly, but other times just trying to come up with findings that will help us make better decisions. And so this will get you to our website, although you can't really take a picture of it, and that's up there. But we do videos, we do public comments, we have these policy briefs, like this one's on TNCs, we've got a bunch of stuff on TNCs. So you can get kind of bottom line, like the research study will have all the details, but you can get kind of like what's the bottom line finding, the implications off of there as well. That's all.
That's the first question from the student.
Yeah. Hi. So yeah,
Second
I
answer.
was curious about like used bets. Because you mentioned like you yourself have one, and you mentioned consumers don't want or like about the chemistry like necessarily that's not going to be useful information for like all consumers. But I think it's really important that they like be confident in buying a used bet, and right now that's like a huge issue. So I was wondering like if not like chemistry lessons, like what would be useful ways to increase like consumers' confidence in buying a used EV. And then I'm also curious like what your experience was like at the dealership, and like did that experience, was it like neutral, or like did they improve your perceptions, or like what sort of information did they provide you, or was it just like here's the remaining range and like have fun?
I see. Okay, so I think my goal wouldn't necessarily be to make consumers confident all the time. My goal would be to match their expectations with what's likely to happen.
Yeah, that's the word I should use.
Yeah. And so I think our one study doesn't answer the question comprehensively enough for me to know what to do with policy, but it certainly raises questions, right? So it seems to suggest that because LFP is living forever, even under abuse, that if you are buying a used vehicle with LFP, it's going to last a long time. Whereas if you have an NMC or MCA battery under abuse, it's not. But what about under the other charging? We don't know. We haven't studied those. So I don't think I also, like I mentioned earlier, we only studied a couple of particular batteries, automotive batteries. A different NMC, battery design might have a different, resilience to. So I don't think we yet know enough to make a policy recommendation where we would try to like tell consumers, for example, that LFP, if you want your battery to last forever, go LFP, and have some kind of like. But right now it's like actually hard for even us researchers to figure out for a given battery electric vehicle which chemistry are they using. I don't know if you guys find that to be true.
These days, you can generally get a pretty good.
Where do you get it?
No, we have the data, but if the consumers know, I don't know. We can know which battery comes with which car in the US.
Yeah, but where do you get that information? Where's the data come from?
I mean, that's not.
Where do we buy it?
It is-
EV volumes.
Okay, so you're buying it.
Well, but you mean which battery is in a particular model?
Yeah.
That's not like hidden information. There's.
Well, like the automakers don't advertise that.
They don't
They call them all
advertise
lithium-ion batteries.
it. Yeah, they don't advertise it, but you
Yeah.
could like Google it. That's pretty easy.
I can definitely look up what somebody said on Wikipedia that it was, but I don't know for sure.
Well, no, so, okay, well, but like, maybe, yeah, so maybe if you go to the like car, like if you go to like Ford.com and you look up like Mach-E, they'll just say lithium ion battery, but like, on Wikipedia, like there's some reference sources on, like news information
Yeah.
on and announcements that have been made. There are like spec sheets that you can find for different, like I haven't.
Yeah, my
really-
experience with it was that, and maybe I'm outdated now, but my experience with it was just pretty spotty. Like sometimes you could find it out and sometimes you could not.
I guess for my EV class, I like looked at a bunch of sources and got a big table for
Okay.
like all the models corresponding to the.
Okay.
I will compare it to a CVT. How many people know what the CVT transmission is on the car? Yeah, so about 4 or 5. But many of us will not buy a car with a CVT
Yeah.
because of the bad reputations.
Yes.
It's more or less the same. You can find it for any car if it's a CVT or other transmission. But it's deep inside.
The frequently asked questions section on Ford.com, their Canadian website, on the Mach-E says it's a lithium-ion battery with nickel, manganese, cobalt cathode, and 68 kilowatt hours.
Very nice. 811 or?
Wow, it's probably a website that only you will get.
I heard gratitude.
I should have. Yeah, maybe thinking about this, maybe a suggestion. So on the policy side of things, there is movement here, right? I think the big one is originally CARB side and now in the EPA rules, deep in the EPA rules, there is requirements for battery warranties and displaying. So all EVs will now have to be able to display a state of health of the battery to customers in a very transparent manner. And so that can help with some of the decision making. And then I think for me, my sense is that the warranty requirements provide enough of an incentive signal to automakers to avoid some of these issues about degradation. But I think, and this was my suggestion to Hannah, was that the paper still makes an important contribution in the sense that it's not really about the degradation of the batteries is going to happen because I think the automakers are already kind of handling that, but that you can point out that different chemistries let you have more flexibility in some ways or others,
Right.
To be able to slam the battery a lot harder with LFTs, right? And I think that is valuable, right? It might be very interesting to see if automakers are already doing that strategy, right? Because we could look at charge curves for cars that have NCA, NMC, and LFP batteries. I mean, you can, if they're not, maybe that's an important decision and say, hey, it looks like you can take better advantage of these batteries. That's
That's a good idea, and I don't know where to get those charge curves, so I'll talk to you.
Yeah.
We
So,
can,
okay,
we
I-
can snip, we can
Alex,
snip
how
that.
like some people
We have a device to monitor the communication on DLC lines. So
Okay.
we can get those.
yeah, so we are at time, so I want to be respectful of all the students' times. Thank you everyone for coming. Jeremy, if can you be around for a couple of
Yeah.
minutes if anyone?
Yeah,
so
sure.
Jeremy will be around for a couple of minutes if people want to continue the conversation, but let's thank him one more time.